Have you ever wondered how computers store and process vast amounts of data efficiently? The answer lies in the clever use of data structures and algorithms, or DSA. Imagine a librarian organizing books. They need a system to store books neatly and find them quickly. This is where data structures come in. A data structure is like a container that holds data in an organized way. Algorithms are the steps a computer takes to solve a problem. Think of it as a recipe. Each step in the recipe represents an instruction that the computer follows to achieve a specific goal. Just as a good recipe ensures a delicious meal, an efficient algorithm helps the computer solve problems quickly and effectively. The choice of data structure and algorithm depends on the problem at hand. Some data structures are better suited for certain tasks than others. For instance, if you need to find a specific book in a library quickly, an organized bookshelf or array would be more efficient than a random pile of books, like a linked list. Understanding DSA is fundamental for any programmer. It's like having a set of tools that allow you to build efficient and elegant software solutions. Just as a carpenter needs to know which tools to use for different carpentry tasks, a programmer needs to know which data structures and algorithms are best suited for different programming challenges. Data structures come in various flavors, each with its strengths and weaknesses. Let's explore some common types. First, we have arrays. Imagine a row of mailboxes, each with a unique number. That's an array. It stores elements of the same data type in contiguous memory locations. Accessing elements in an array is super fast because you can directly jump to any location using its index, just like knowing the mailbox number. Next, we have linked lists. Think of a treasure hunt where each clue leads to the next. In a linked list, each element or node points to the next one in line. This structure is flexible for inserting and deleting elements, as you only need to change the pointers instead of shifting the whole structure like in an array. Then there are stacks. Picture a stack of plates. You can only add or remove plates from the top. This is the LIFO, or last in, first out principle of stacks. They're handy for tasks like tracking function calls in a program or implementing an undo feature. Queues are another type. Imagine a line at a ticket counter. The first person in line is the first one to get a ticket. This is the FIFO, or first in, first out principle of queues. They're used in task scheduling, handling requests in the order they arrive, and more. Trees are also important. Think of a family tree. It starts with a root or ancestor and branches out to children, grandchildren, and so on. Trees are hierarchical structures that are great for representing hierarchical data and for efficient searching and sorting operations. Lastly, we have graphs. Imagine a network of cities connected by roads. Graphs represent relationships between entities using nodes or cities and edges or roads. They are used in social networks, GPS navigation systems, and various other applications where relationships between objects are crucial. Algorithms are the workhorses of computer science, providing step-by-step instructions to solve problems. Let's delve into some key algorithm categories. First, we have sorting algorithms. Imagine arranging a deck of cards in order. Sorting algorithms do precisely that with data. They arrange elements in a specific order, such as ascending or descending. Popular sorting algorithms include bubble sort, insertion sort, merge sort, and quicksort. Each algorithm has its own trade-offs in terms of efficiency and complexity. Then we have searching algorithms. Finding a needle in a haystack is a classic search problem. Searching algorithms efficiently locate specific elements within a dataset. Linear search goes through each element one by one, while binary search works on sorted data, repeatedly dividing the search space in half, making it much faster for large datasets. Next, there are graph algorithms. These algorithms deal with problems related to graphs, such as finding the shortest path between two nodes, like Dijkstra's algorithm, determining if a graph is connected, or finding cycles within a graph. These algorithms have applications in GPS navigation, network routing, and social network analysis. Dynamic programming is another category. Imagine solving a complex problem by breaking it down into smaller, overlapping subproblems. Dynamic programming tackles problems by storing and reusing the solutions to these subproblems, avoiding redundant computations. This approach is particularly useful for optimization problems, like finding the shortest path or the most profitable way to pack a knapsack. Finally, we have greedy algorithms. These algorithms make locally optimal choices at each step, hoping to find a globally optimal solution. While they don't always guarantee the absolute best solution, they often provide efficient solutions for a wide range of problems, such as activity selection, Huffman coding, and finding the minimum spanning tree of a graph. Not all algorithms are created equal. Some are faster and more efficient than others. To compare algorithms, we use the concepts of time and space complexity. Time complexity measures how the execution time of an algorithm increases as the input size grows. It's like comparing how long it takes to cook a small meal versus a feast. A good algorithm has a low time complexity, meaning it can handle large inputs without taking forever. Space complexity, on the other hand, quantifies the amount of memory an algorithm uses relative to the input size. It's like comparing the size of the kitchen counter space needed to prepare a simple dish versus a complex recipe. An efficient algorithm keeps its memory usage in check, especially when dealing with massive data sets. Big O notation, a mathematical notation, helps express the upper bound of an algorithm's time or space complexity. For example, O of n means the complexity grows linearly with the input size n, while O of n squared indicates quadratic growth. Understanding complexity helps programmers choose the most efficient algorithms for their specific needs. Section 5. The importance of DSA in problem solving. DSA is the backbone of problem solving in computer science. It provides a structured approach to tackling challenges. 1. Problem definition. Clearly understanding the problem is the first step. This involves identifying the input, the desired output, and any constraints. 2. Data structure selection. Choosing the appropriate data structure to represent the data is crucial. The right data structure can significantly impact the efficiency of the solution. 3. Algorithm design. This step involves devising a step-by-step procedure to solve the problem, often leveraging existing algorithms or creating new ones. 4. Implementation and testing. Once the algorithm is designed, it's time to implement it in a programming language and thoroughly test it to ensure correctness and efficiency. By following this structured approach, programmers can break down complex problems into manageable steps, leading to robust and optimized solutions. Section 6. DSA in competitive programming and job interviews. DSA is paramount in the world of competitive programming and technical job interviews. In coding competitions, participants are challenged to solve algorithmic problems within tight time limits. Mastering DSA is essential for devising efficient solutions that can pass all test cases. Technical job interviews, particularly at tech companies, often involve coding challenges that assess a candidate's understanding of DSA. Interviewers use these challenges to gauge a candidate's problem-solving skills, coding proficiency, and ability to think critically under pressure. Preparing for these scenarios involves practicing on coding platforms like LeetCode, HackerRank, and Codeforces, where you can solve a wide range of algorithmic problems and hone your DSA skills. Section 7. Real-world applications of DSA. DSA is not limited to theoretical concepts. It has a profound impact on various real-world applications. For instance, databases heavily rely on data structures like B-trees and hash tables for efficient data storage, retrieval, and indexing. These structures enable databases to handle massive amounts of data and perform quick searches. GPS navigation systems and network routing protocols employ graph algorithms like Dijkstra's algorithm to find the shortest paths between locations, ensuring efficient data transmission and route optimization. Search engines like Google use web crawlers that traverse the web, following links to discover and index new web pages. These crawlers rely on graph algorithms to explore the vast network of web pages efficiently. Moreover, AI algorithms, particularly in machine learning, leverage DSA extensively. For instance, decision trees are used for classification tasks, while neural networks rely on interconnected nodes and weighted edges, showcasing the importance of graphs in AI. Section 8. Scalability and resource optimization. In today's data-driven world, scalability and resource optimization are paramount. DSA plays a vital role in building systems that can handle massive datasets and operate efficiently. As data volumes increase, choosing the right data structures and algorithms becomes crucial for maintaining system performance. Efficient algorithms ensure that processing time and resource consumption grow at a manageable rate as the data scales. Memory and processing power are limited resources. DSA helps optimize their utilization by choosing data structures that minimize memory footprint and algorithms that reduce the number of operations, leading to faster execution times. By carefully considering DSA principles, developers can create systems that can gracefully handle future growth and make the most of available resources. Section 9. Conclusion: DSA, a foundation for success. Mastering data structures and algorithms is not just about acing coding interviews or winning programming competitions. It's about developing a strong foundation for a successful career in software development. DSA provides a set of tools and techniques for approaching problems systematically, writing efficient code, and building scalable systems. It empowers programmers to think critically, analyze trade-offs, and design solutions that are both elegant and practical. In a world increasingly reliant on software and data, a strong grasp of DSA is an invaluable asset. Whether you're building web applications, analyzing data, or developing cutting-edge AI systems, DSA will be your constant companion, guiding you towards efficient and optimized solutions.